Ricardo's here on the call. And this complexity results, amongst others, from the case that everything comes together on that level. So you have to handle the normal task, the happy case. You have to handle contingencies, so not failures, but issues that happen in the interaction with the real world, like the robot loses position, or an object that it tried to grasp falls from the gripper, or similar things. And of course, then system level errors, like a LiDAR sensor fails, or a motor is not working, where you then really have to switch to degraded modes. And all this in parallel, because this layer triggers multiple skills in parallel in general to run the actual mission. That's difficult to test, this layer, time consuming. Developers either use the real robot or very complex setups in simulation. It lacks of reproducibility, especially if we want to test certain edge cases. And it's also desired or appropriate to have some kind of adequate representation of the world around the robot. Again, here the information from multiple sensors comes together. It has to be diffused to some degree, perhaps also cleaned up, that you have a consistent view on the world to be able then to make decisions based on this representation. And since robots are typically deployed in a certain environment over a longer time, you also want to have some adaptability on that level, that the robot learns over time, is able to understand how it has perhaps to change a mission or a task to be more successful. So to have some kind of task level learning here. Now, if we look again at technologies, and here I try to distinguish between some executive layer, which actually executes the task, and some planning layer. You can draw a picture like that here. So on the left-hand side, the technologies where, let's say, the tasks, the missions are somehow pre-programmed, either by finite state machines, scripting languages, or in some kind of hierarchical fashion. I would say then there's perhaps the goal of the whole planning community to come up with a comprehensive planning mechanism where you have your representation of the world, a kind of goal description, and then can automatically derive the whole plan to achieve this goal. And in practice, you see a combined approach in between, where, let's say, some environment model plus dedicated reasoning mechanisms working perhaps on partially pre-programmed tasks are used to implement these complex missions. These reasonings may be, of course, classical planning technologies, could be also some kind of machine learning, could be simulation. And you see here in this spectrum also the balance between pre-programming and planning-based approaches, where I would say with pre-programming it's easier to understand, it's faster. Of course, you run into kind of combinatorial explosion if you want to implement a lot of edge cases. A planning-based approach lacks perhaps of scalability. If you really try to put everything in one single planning problem, requires a lot of expertise. And I think this spectrum is seen also in the many technologies that are available for this layer. The planning-based approach has strong roots. Here I depicted Shaky, the robot, can see not live, but as an object in the Computer Science Museum in California, and in Sunnyvale Computer History Museum, that already use TRIPS, the Stanford Research Institute Problem Solver, which is the precursor of PDDL, which is still developed, especially by the ICAPS community. So using classical AI methods with robotics is not new. That has its roots in the very first robots. I like this graphics here from colleagues who wrote a survey paper on domain-specific languages to illustrate this complexity by numbers. What they did, they analyzed domain-specific languages that have been proposed for robotics, and classified them, and found out that most of the languages somehow are about the architecture or about this reasoning on the deliberation layer. So this graphics already illustrates this problem that there is such a large variety, which is to some degree an indicator that a gold solution, a proper solution, has not been found yet, or that many solutions are required depending on the actual use case. And if we look now in ROS2, we have also quite a slew of technologies available. There is SMAC, you know, there's PlanSys2. Happy to have the developers here also in the call. Behavior tree, David is also here. Merlin 2, for example. Yasmin, FlexB, more known from ROS1, but has recently been also ported to ROS2. And I think if we search further, there are many more technologies available. So that's an indicator that also in the ROS context, we have many solutions. And the idea of this working group is to bring the developers together and to think about, perhaps also to some degree, to streamline this and to bring these developments together instead of having many competing technologies. 2 slides on the EU-funded project that is behind this initiative. The goal of Convince is to research directly in this field and especially to develop model checking techniques to speed up the testing and verification process of this deliberation layer in robotics applications. We look into 3 use cases: vacuum robots, manipulation, and here museum guide. So by design, a very diverse spectrum of use cases to have as many as requirements as possible. More concretely, we work on the planning techniques themselves and make them also adaptive in the sense that they allow the robot to adapt over time to its environment. On tools for this model checking, and finally, one goal is also to integrate these tools in an open source software tool chain, and ROS plays, of course, an important role for that, and that's why we want also to reach out to the community as early as possible. If you're interested in more information about the EU project, which shall not be in the focus of this working group, of course, go to convince-project.eu. And here you find also the list of partners. Most of them are present in today's talk. You see here from Bosch, the lead is with the IIT in Italy, University of Genoa, brings a lot of knowledge on the model checking, CEA on the modeling tools, and University of Birmingham for the planning side. With that, I would like to conclude my introduction and then hand over to Christian. Sure, you can get it. Thank you very much.
Ich fand jetzt sehr interessant, dass du da. Ich habe ja auch gerade erst abgestimmt.
I am here. Can you hear me? Yeah, it appears that the share button is muted. I can't share. Can you enable that for me? And again, I'd like to keep my presentation interactive as well. So thank you very much. So I just put together.
Presenter, you should be already able to present now.
Yeah, I see that.
Yeah,
can you guys see the slide?
Yeah. Yeah.
Perfect. Okay, great. So as I said, I'd like to keep this interactive as well. I just prepared a couple of slides to talk about Imandra and the role that we want to play in this activity. We're very excited that this working group's getting kicked off. So I would be surprised if many of you had heard of Imandra or worked with us. I know some of you have, and some of you were actively working with. But Imandra is a company that does automated reasoning based on functional programming and symbolic AI to do formal verification of software systems, as well as address complex logic problems. So we work a great deal with the Department of Defense here in the United States on autonomous systems. We also do a great deal of work with financial institutions. So helping large banks formally verify their trading engines and also handle verification of their communication systems. And we've done all kinds of rule synthesis and complex logic problems. So this mission planning, mission layer, deliberation layer, we think is well suited to symbolic AI and automated reasoning. So here's an example of 4 applications in the autonomous system space that we're actively doing and making investments in. The first one is we've got an example on our website that I'm going to walk through in just a minute that you can interact with in a Jupyter notebook that does formal verification of a very, very simple ROS control node. And I'm going to show you some of the details of that in just a moment. We also have built technology to do black box discovery of systems within a larger system or within a network of nodes. This is a very useful technology set for discovering properties of existing systems, or when a system needs to be updated, analyzing the system as a whole to take a look at what has changed. So this is critical when something is formally verified and then an update happens to understand exactly what has changed. You don't have to re-verify the entire system. The third is scenario-based testing. We have technology for synthesizing unique scenarios that could be fed into a simulator to find a complete set of critical scenarios for testing. This is a little bit more of an autonomous vehicle capability than it is for robotics, but we know that this is a blurring space between robotics and autonomous vehicles. And then the other piece that we're working on, where we've done some initial work and it's pretty early in our process, is around verification of mission plans for robotics. And we are very excited about developing formal semantics around behavior trees or whatever high-level language this group believes should be used for doing mission planning and that deliberation. So here, let me just show you a little bit about the workflow of our tools at the lowest level. This is kind of the lowest level interface that someone might use. And what we have here is this very, very simple robot. All this robot is a 2-wheel robot with 1 sensor. So it couldn't be much simpler than this. And the robot simply looks if there's an open path. If there is an open path, it moves forward. If it isn't an open path, it stops, rotates, and starts moving forward again. So this is the type of software that there's so simple, you know, how could you have a mistake in software like this? We have this example up on our website that you could play with and take a look at. And in this demo or workbook that's available, we actually do verification of 3 verification goals and implement formal verification. Now, the code you see here is an implementation of the ROS node using a language that is based on OCaml, which is a functional programming language. And we have tools to help with the synthesis of the OCaml code. So code was based on Python or some other language, bringing it into the OCaml environment, which we have a restricted version we call a Imandra modeling language. Is a pretty straightforward process. But we create a verification goal and ask the question, is there ever a state within the software where there could be an object within 0.2 meters of the robot and the robot doesn't stop? So we attempt to formally verify that the robot will stop when an object's within 0.2 meters. And we actually get back that it's refuted, that there is a state in the software where the robot will not stop when there's an object within 0.2 meters of the robot. And that's an edge case in the code where if the LiDAR system was ever to return an empty list for any reason, then the robot won't stop. This is clearly the type of software bug or software defect that can be managed, but it slipped through as an edge case that wasn't properly handled. And I know we've all been involved in much, much more complicated systems where these edge cases can slip through. So this process of modeling the environment and performing formal verification on it can help us find these types of edge cases before the robots get into the wild. But now, if we suppress that empty list use case, we actually go back, formally verify, and prove that the robot will always stop for every possible input from every possible sensor and every possible state of the software. And one of the reasons that we can be confident is we have a technology at Imandra that's called region decomposition, which allows us to take an infinite state space and break it down into a finite collection of states where each one is invariant. So there may be an infinite number of parameters that can push you through these individual states, but each one of these states is unique and invariant. And some of them have an infinite number of possible parameters or inputs, values going into them. This particular simple robot, the control node that we saw, has 18 unique states within the software. So it's a pretty simple one. This can scale up to hundreds, thousands, tens of thousands of unique states. So this could be used to generate a unit framework, test framework for a node within ROS, because we can use this approach to identify all the unique cases and then push the software, the control software, the production software into those unique states to make sure that they're operating correctly and ensure complete coverage. Now, we are doing some things with large language models, ChatGPT, to make this a little bit more of an interactive approach and less of a programmatic approach. And that's work in progress. We've made a lot of progress on the financial side. We can give a demo to people on that at some point. All right, so two more slides. So for this particular group, you know, we are very interested in creating formal semantics around whatever environment or language that we choose for this planning layer. This would allow us to reason about that layer, ask questions, prove properties, perhaps during edit time, as well as during deployment time of the software system. By verifying those goals, we could explore all possible actions that the robot could take and make sure that we remain in a safe region. We can ask questions about the flow of execution. If by building your mission plan, you may want to know what are the possible paths to get to this node within my system, or what possible places can we go from here moving forward. And we think this can scale to systems, you know, mission plans for fleets of robots that are out there doing delivery processes or managing delivery of equipment within a building or a community or what have you. So with that, I'll take a breath and ask if there are any questions or comments about what I've shown here today.
Yeah, so from my side, thank you very much. Can you say a bit more about which part of the system you plan to test? Because in this slide number 2, that indicated that you're really looking into verifying the whole software underneath. At the end, you mentioned now that you would like to focus on the behavior trees. Let's say where the scalability issues or the borders for your testing approach.
Yeah, so for the tools that we're building, we believe that we can add the most value, the quickest, in a more general way at the behavior tree layer or the mission planning layer. Now, we have examples of going all the way down into the control code, the embedded code that would run on the robot and govern the control of the actions of the robots. That's pretty tailored. That's pretty, unique development, working with the customer each time. But creating high-level tooling at the behavior tree level is something that's very interesting to us. We think that the market is going to continue to evolve to a standard mission planning software framework across the industry. Behavior tree seems like the top candidate right now. So we want to have tooling around automated reasoning and formal verification for that language, for that approach. Did I answer your question, Rolf?
Yep, that answers it. Thank you.
Yeah, perfect. So to be really succinct, the behavior tree level, the mission planning level, that's the priority. But we could model a control node right now and work hand in glove with the customer and help them verify a control node if that's what they wanted to do. Okay, we have a question from Lorenzo, it looks like.
Yes, thank you very much for the nice presentation. I was wondering if you plan to verify software involving multiple components, like gross components, and not just a single piece compiled together, piece of software compiled, same executable.
Yeah, absolutely. So that's when we work a lot with our DoD customers. I can't get into too much detail, but there are interactive software components, very similar to a raw system where you would have multiple nodes. We could model multiple nodes within a system, or we can just observe multiple nodes and create sort of black box implementations, or learn about black boxes within a larger robotic system. So there could be a blend of opaque software and software that we have more exposure to, but try to verify systems of systems that way. And we have a particular research project that we're hoping that moves forward, where we'll be doing just that with another government institution here in the States. So yeah, I think that we can do both, and we're interested in doing both. And I'd love to understand what's behind the question, maybe offline, if you have a thought or an idea or a problem you'd like to see us address. Thank you for the question. Great. All right, Christian, should I will stop sharing. How does that sound? Great. Yeah, that's a really good question. So I've been digging into the robotics marketplace a lot over the past couple of years. So my background, just to give everybody a little bit of context, I worked at National Instruments for 25 years, and I ran their smart machines, Industry 4.0 business for 6 years of that. And then I pivoted to autonomous vehicles. Now, I believe that we're in a transition within the robotics marketplace where today safety is handled with a fairly, I would say, as a blunt tool, where robots are kept away from people, or if robots get close to anything, they stop. So the level of sophistication and safety is pretty low to maximize a safe work environment for workers. As we move forward, when we have more cooperative robots, we have more mobile robots moving faster on the sidewalks and the roads, this need for verifying safety systems is going to increase. And we have a lot of conversations going on with people doing faster logistical robots, things like forklifts, people that are doing agricultural equipment, and talking with people that are doing robotic systems in the medical space. These are the conversations that are pretty early, but those are the types of conversations we're having. Thank you.
Thank you. I'm going to share my screen. On my screen here. Do you see my screen now? Yeah. Okay. Yes. So I would like to talk about the deliberation acting with PlanSys2. I'm full professor at the Rico University, where I lead the Intelligent Robotics Lab. I have done many projects, and I would like to highlight this one in the left bottom part. This was a project we had with a company, with Acciona. We use planning and behavior trees to do a robot that attend the people that visit the places. There are another works around here that uses planning, but this is one of the more highlighted project for this topic. As I see this part, I think I very agree with what Ralph said at initial. I also divide this in mission, task, what he said, executive, and skills. And I would like to talk about this. In the first part, I would like to start with the part of the task. So for the task, I usually use the finite state machine. This is a finite state machine for bump and go, for example. That with this finite state machine, you can create very easy behaviors, and also you can use behavior trees. So I think everybody now knows behavior trees. This is a mathematical formalization of it's a tool to create behaviors, to create control. This is a video of Moses. I think this is for I don't remember I think this was created by Davide Faconti. Not only the library, but also the demo. He collaborated with
University of Ulm together.
Yeah. Yeah. So you can create a lot of tasks using very powerful tasks using behavior trees. This is a screenshot of Groot. That is a tool for behavior trees. I think many of you know it. As I see, behavior trees is not for coding directly the everything or the control from the top to the down, but it's also intended to control subsystems. You can read the values from the driver of the robot or even sending command, but it is best use controlling subsystem like navigation or manipulation. Jumping from finite state machine to behavior trees is more or less direct. It's not the same, but can be more or less direct. I prefer to work in the last years with behavior tree. I think it's better. It captures better the task that the robot has to do. In this part, in the second part, I would like to talk about this part of the mission. In the mission, we have planning and also cognitive architecture. I would like to say something about that. Planning, as you know, is you have a current state, you need a goal state, and this is automatically calculated. That is the difference with respect the behavior to a finite state machine, which you say the robot what to do in each moment depending on the sensors or the other perception. So this can be automatically calculated. So you start from a domain, from a problem, you use typically a PDDL planner, and you get a plan. Okay, so this is plan. So why do we need a planning system? okay, to bring the AI planning to the real world. So you have a mechanism to read the model, to update the knowledge that we have, symbolic model, to create that plan, to usually calling to a PDDL planner. And this is the most important, they execute the plan. To execute the plan, you also need implementation of the action that are in the PDDL with real effects. And you also need tools to monitor, to control, to debug the system. My work in PlanSys2 is very related to ROSplan. ROSplan was a very successful software, very nice software for Roll1, but unfortunately they did not take the step to go to ROS2. So I created a ROS2 planning system. ROS2 planning system is a framework for e-planning inspired in ROSplan with a modular design. Here you have the main modules of the system and many features. Here you have a diagram of PlanSys2 is divided in several nodes. Each component you see here in the left part are nodes. You have a domain expert in which you read the domain and you can validate the operation of the system. If a predicate is valid, exists, the type is correct, something like that. You have a problem expert in which you store the knowledge of the raw nodes. You have planner, which takes the information from the domain, from the problem, and calls for different planners. For example, POPIF or fast don't war. You call it, you create a plan, and and the executor take that plan, converts it to a behavior tree, and execute a plan. In the right part of this image, you can see several applications. The applications are composed by the implementation by the PDDL domain that you have to provide this, and the implementation of each action, and also an application that controls the execution. It initialize the knowledge, and also call the executor to create the plan, verify that the plan is executing correctly, and ask for a replanning if something went wrong. So this is PlanSys2. We have tools like PlanSys2 Terminal. This is a Unix-like tool for like a terminal to manipulate, to get information, to run, to do anything you want with PlanSys2. So it has some characteristics. It's reliable because it uses DDS, uses lifecycle nodes. Also is very modular because each of these modules can be replaced. For example, in this project that we did with the people of AIPlan4EU, we replaced the planner, the domain expert, and planner expert with a UPF version of them. So instead of using the planner, regular planner, we communicate with UPF using a node that we developed in that project, in a project funded by them, called UPF for ROS2, and we use this. Okay. We call the plan as behavior tree to execute it. We support multi-robot because we can deploy the action in several robots and, for example, specialize each action depending on, for example, the argument. If the robot of that request or the action you have to execute, say the robot is Tiago 1, so you execute the navigation in Tiago 1. Or for example, you have to pick something, it's a box. Maybe you have action specialized for each object. So it's specialized, it's multi-robot. We have a mechanism to deliver this action. You have here the executor node. When you have to execute one action, you do like a binding. So you say, okay, who can do this action? And the action that think that they are the correct election to execute that action, they bid for the action. You select one and start executing. So this is a protocol we created. I think it's much more flexible than using ROS2 actions. It's very efficient, much more than a ROS plan, and it produces a lot of information. It has a lot of topics that produce a lot of information. This is an example of PlanSys2 executing. This is a simple example of integrating PlanSys2 with navigation, but also I have used this video to show you the tools that are available. A part of the terminal that you see here in the left bottom part, you have RQT application to see the plan, to see the status of the action performers, and also to see the knowledge that has the PlanSys2 inside. So this is one video. Another video is when we published PlanSys2 in, I think it was IROS 2 years ago. We did this experiment in which the robot had to simulate to cook some dishes. So this is the cook, this is the fridge, so there's a different part, and the robot was working around 3 hours doing this. So it was done to show the robustness of PlanSys2 with replanning, plans failing, and everything. This is a video of my student. This was recorded this week, in which they used the PlanSys2 to solve one test in the RoboCab at home. So it showed that it's very easy to use PlanSys2 even for grade students. They have to clean a house, and if grandma asks you for something, for example, for her glasses, the robot has to abort the plan, replan, and bring the glasses to the grandmother and continue. So they did this nice video. This was a student. There were people with 20 years old, and it was very nice. The video is very long, so I will pass. We also use this software for a competition for Mitocaine, in which I would like to talk about cognitive architecture, because cognitive architecture, I think, is also an important part of the deliberation. It's something more than intelligent architecture or a control architecture in which the robot has more high-level capabilities. This is our architecture, in which we have a layer with planning, the action, the skills. In this part, you have the mission, in which you select in which moment what is the goal. But also, this cognitive architecture has a central cognitive part that was a graph, a knowledge graph, in which everything, even the robot, was represented here. And changing these arcs, you can, for example, trigger the conversation, or trigger, for example, I don't see here the need to see something, to activate to focus to move the neck of the robot to see something. Also, I would like to present another architecture is CoreSense. Well, this is an European project that has just started. CoreSense is an hybrid cognitive architecture for deep understanding. So if you want to check it out, it's here, the URL. We are involved here with our experience in ROS and cognitive. So I think this is also very interesting. And the last part is about the skills, but I think everybody knows, for example, Navigation 2. This is the video of Navigation 2, the marathon. I will pass this very fast. This is the part of the skills. I will pass this very fast. This is the experiment of this skill. And that's all. Thank you for your attention.
Thank you very much. Also from my side, Francisco, I know the two questions First one is you showed that from the planning side you can either trigger direct actions or also other behavior trees. Do you have some kind of generic interface how to then trigger behavior trees? How is this technically done? And the second question is, can you say some more words about UPF that was shown on one slide?
Yeah, I will show you again. We go to a slide.
For the second question, it's the presentation, the next presentation.
Okay, okay. I thought about it. Google already found that it relates to AIPlan4EU. Then we wait for that later. Yeah.
Yeah. About the first questions, yeah, I went very fast for that part. A part of using behavior trees for the execution to go the plan, inside the action, the implementation of the action, you can all the action inherit are classes, roster nodes that inherit from a common interface, and you can program it directly, or you can specify a behavior tree. So it's very direct. It's very direct because you use a generic PlanSys2 action in which in parameter you give the plugins to load for the PT nodes and the XML to execute. So it's very easy to use it. So this is more or less the deliberative part, and the action could be the executive part using whatever you want, for example, behavior. Yeah.
And what's behind this actions hub? Is it more than
it's a topic.
The list of, or is it some dedicated component or additional functionality on? No.
It's a topic.
It's a topic. One single. Okay.
Yeah, so I designed a protocol with some messages. All the components are subscribed and published here and implement this protocol.
Perfect. Gianni, you have also a question.
Yeah, thank you for the presentation. I have a question about the multi-robot part. So how do you model the fact that the different robots may have different capabilities? And maybe also being able to execute the same skill, but maybe not with the same goal. So, for example, the age of an object that cannot be reached or can be reached depending on the robot.
Yeah, it's multi-robot, but it's a centralized. It's centralized. So you have an instance of PlanSys2. And this is done in a simple way. So each robot has their own software with their navigation, their movie, tour, or whatever. And usually when I create a domain, in the action, I add a parameter that the robot has to perform the action. So as everybody, all the robots are listening in the action hub, if you include this parameter of the robot, the action can apply for executing that action depending of this argument. So that's the way in which we can get a multi-robot. The action, the specialized action, depending on the object, it's also telling which parameter this action are interested on. So it's very simple. It's a very simple way, but it works.
Thank you.
Thank you.
Yes, I have one other question. So this presentation shows some really cool applications for basically using PlanSys2 as the orchestrator of everything. I'm wondering how easy is it to go the other way? So say you have some already built up software framework where you want to use PlanSys to query a request for a plan, and you get back a plan that you can then manipulate yourself. So for example, it returns to you a behavior tree that you can reuse in other modules.
What is exactly the question? Sorry.
Oh, if there's a way to, instead of having PlanSys2 be the central orchestrator, that you can use it more as like a service to request a plan, get back some, behavior tree that you can then take into another system.
Yeah, I think you can do it. You can do it. Yeah, I don't know. I don't know how to say that. Sorry, Sebastian.
Thank you.
You are mute, Ralph.
Yeah, it's Maji, actually. Thank you, Paco, for your presentation. I would like to have few words about this cognitive architecture that you were proposing, and specifically I wanted to know if you are using some learning techniques to acquire this graph or this kind of ontology that you showed.
No, and that is a very good question. No, we are not using learning. We are not using ontology, but in fact, I think this is the next step, is using one ontology to give consistency to this graph. I think in core sense, I'm sure we will do it because we are working with the people of TU with Carlos Corbato, and he's an expert in ontologies, and maybe we could advance in that part. But no, we have a central part, a central component, only with nodes, with arc, and that's all.
Okay, thank you.
Thank you.
Hi, Christian. I have a question about the behavior tree that is used by the planner. Does the planner construct these trees dynamically, or they are predefined?
Yep. We have a paper about that published in AMAS that describe all the process. But when the executor, when get the plan, it's a list of action. It creates a graph with the plan, a planning graph, and from this planning graph, it creates the behavior tree. So for each plan, there is a behavior tree, and it is fixed. It's static. It does not change with time. If the behavior tree fails, if the plan fails, when you create another plan, you create also a behavior tree that encode that plan.
A follow-up question to that: how much effort is there to debug any, I guess, failure encounter while executing the behavior trees?
Yeah. It's not well. It was quite well. It produced a lot of information, and even the subtree that represent an action that is to check the requirement, to apply the effects and everything. You can also add more BT nodes to help you to debug. So you can do it in that way. But I think as far as I have done with this, it is not necessary much mechanism to debug this. If the plan is correct, usually the behavior tree is also correct.
Thank you.
Thank you. Thank you.
Yeah, it's always like that. Can you see my screen? Nice to meet you. Okay, perfect. Thank you so much for giving me the occasion to talk here. Nice to meet you. I'm Guglielmo. I work at Magazino, and yeah, I wanted to say a couple of words about AIPlan4EU. I thought that it would what we are doing this project could interest you, and that's why yeah, this morning I was like, okay, let's maybe spend 10 minutes on saying a couple of words. Okay, so this European project is a collaboration between multiple partners. Yep. Okay, hold on a second. Is it working now?
Yeah, now we see the slides.
Okay. Okay. I was saying that this project is collaboration of different European partners, and in particular in this project we have different research institutes. The lead institute is FPK, so the Bruno Kessler Foundation in Italy, but then we have other universities like GLAS, the FKI, or the University of Basel, Brescia, La Sapienza. In this project, we are Magazino, one of the companies that is bringing to the table use cases to be applied to the planning domains. So what we are doing as Magazino, as a company, I don't know if you know us, but basically we're a robotic company located in Munich, roughly 120 employees that is developing robots. So we have Toto and Soto. There are two robots that are working respectively in the e-commerce and in production environments. This project starts from basically the idea of planning, right? So we have we model a system, and we have a goal that we want to reach, and we want to find a course of actions to drive the system to the goal. And basically, what has been noticed in the past by especially the people at FPK is that every planner is currently pretty difficult and it's very different. It's not trivial to integrate it into a system. This is one of the maybe question that for example, Sebastian was asking this, I guess, because there is an interest, I guess, in the robotic community to have easy to use planners for robotics. And so in this particular project, the idea is to, the goal is to make planning accessible to basically practitioners and innovators, facilitate the integration of planning, making planning relevant in diverse application sectors, and integrate planning within the AIPlan4EU platform. So Ralph had a question of what this is about. So the idea is to have develop a unified planning framework, which is bluntly speaking, or really simply speaking, is a Python library that can be used also in other languages through bindings to be able that abstract away a planner. And in this particular project, the goal of this project is to develop this unified planning framework, as well as a set of planning engines that can be readily used by the different universities. And also, the goal is to collect a bunch of use cases throughout different areas of industry to actually understand what are the planning problems and describe the different properties that the planners that we need to integrate into unified planning framework need to have in order to be able to have a general framework that can be used for as a basis to develop and integrate whatever planning engine. So connect it to some extent the use cases with actually the solution providers, which are the planning engines. Okay. So about the unified planning framework, it's actually already online on GitHub. Here I just it's written in Python, and here you can see kind of an example of what you could expect. So it's basically a Python library that you can use in order to specify your planning problems, and then you can register planners and choose whatever planner and get a result out of it. So it's under development. They are trying, so here we're trying to reach the version 1.0 of the library in June, but it's currently, we are version 0.6, and it's pretty solid and working already. So if you're interested in it, go check it out here. So this is the first message that I wanted to share with you today. Also, what I wanted to share with you, which might be of interest, is what we're doing in this particular project. And the contribution that we're bringing to the table is twofold. So here we are bringing our two robots to the table, to the project, and we have analyzed two aspects of planning combined with behavior trees. So these two robots are actually fully autonomous robots that are working every day in warehouses or production lines alongside humans, and they're controlled by behavior trees. And in this project, we are analyzing how we can use planning technologies in two aspects. First of all, what exactly Francisco was mentioning. So in collaboration with Francisco, we have been developing this wrapper around this Python library, which is in ROS. So currently there is a version in ROS 1 and ROS 2 that you can already use today. And here, maybe Ralph, to answer what you were asking here, there are a bunch of services and actions that are exposed, and you can register this this framework and use it as a standalone. Maybe also connecting to what Sebastian was asking. So this could be a way, for example, using the planning let's say capabilities of the framework without having to use the entire engine. So here it's just the idea is to have a way to interface directly to the planners by you give it a goal and you just treat it as an oracle, you get an answer. Okay, so here the idea here is that we are describing problems as PDDL problems. The library actually abstracts away from the planning description language. But here to interface it with ROS, so Francisco actually was the original developer here. We decided to go with PDDL. So here, if someone would think about integrating this, we thought, okay, this library could be a first entry point to use this library. And if more advanced features are needed that are outside PDDL, for example, we discovered that we were needing it, one can use directly the library or write its own wrapper. So this is the idea is to have an easy entry wrapper for this entire framework. So it's this planning framework is usable via ROS actions, and it's compatible. Actually, these interfaces here have been designed by Francisco, and they are basically fully compatible with PlanSys2, both in ROS 1 and ROS 2. So this is the first thing that we brought to the table. So we are pushing this wrapper, ROS wrapper, and we use that to actually condition our behavior trees that they are running on our robots. The second part that I thought maybe would be interesting for you is a publication at ICAPS 2023. So it's coming up soon. It's a second part of the work that we've been doing at AIPlan4EU. This was in collaboration with the University of Örebro, Alessandro Saffiotti and his team. And here we have been using planning technologies offline to actually validate behavior trees. So in Magazino, we have a really huge behavior trees. And we have been struggling sometimes with bugs and issues, and as every, let's say, companies. So we have been developing together with Örebro a way of validating. So using planning to validate the behavior trees, identify possible execution that may violate given data or ordering constraints, and also exhibit traces of or examples of these wrong executions to help debugging. So this was the user. Also in this paper, it might be interesting for you to have some insights of our formulation of behavior trees. So we are currently using a proprietary formulation of behavior trees. We have a couple of patents that you can read online. They're actually linked to this particular paper, but I thought that it might be interesting for the community to know what we are doing here. Okay, so that is all. I just wanted to take the occasion to present, say a couple of words of what we're doing, and I would like to thank you for your attention. If there are any questions up here. This one? Oh. Yeah, this is all proprietary too. Yes.
Yeah, I have a quick question about that proprietary tool and whether or not there's a easy way to export and import behavior trees for
Yes.
analysis and synthesis, and if that's documented online anywhere in that format.
Yeah. So I have to double check in the paper, but trees here are represented as JSON files that actually can be imported and exported in the tree. And actually, these JSON files are the one that have been shared with the University of Örebro, and the planning and the validation has been done exactly on this particular JSON files.
Okay, perfect. Thank you.
No problem. Jamie, if it's not on the paper, you can contact me. I can send you actually the preprint if you want of the paper, and we can, if you're interested, I can share maybe an example of the.
I'm super interested. So yeah, I will reach out to you. Thank you.
Okay, I'll stop sharing. Thank you so much.
You could maybe even call it the roots of the discussion. It's a single select. Yeah, we might want to change that because there's a few days that work better for me than others. I can do any day. This is important stuff. Is there a desire to do a face-to-face at the ROSCON meeting in New Orleans? It's pretty early. I guess that's in like, when is it? Is it October? I can't remember when it is. I don't know. I'm just throwing it out as an idea. I think that we could talk about it offline. It could even be informal, right? We could just all, those that are there, we could get together and kind of get to know each other a little bit in person.
Invite for this. Yeah. No, but that's exactly what ROSCON is for, and there's always via the app or website you can always announce also such meetups. Yeah.
Yes, just a late question for Francisco about the PlanSys framework. I was wondering if there are plans to support also other formalism like hierarchical task networks, and if there are plans or work in progress to integrate or create some links with task and motion planning approaches, like for example PDDL stream, which is a framework that I think also Sebastian, who is here, has presented in a past talk. Ralph, you are muted. Okay.
Yeah. Hi, Matteo. No,
Hi.
there are plans to extend PDDL to hierarchical planning. But well, now that we have integrated with UPF and UPF support hierarchical planning, maybe I could start thinking about that. But there are no in the plans right now. And the other question was about PDDL stream. I have to check it out. I have to check it because I think it's also a nice tool, but I haven't tested.
Yeah, I was wondering if we can use this working group as a medium to foster interactions, eventually also collaborations around these topics.
Because I'm sure
Yeah,
that's
I
where.
wanted to say the combination of UPF on, let's say, on the planning part with some generic mechanism to connect to the skills layer, or which is to some degree implemented by you already, Francisco, in PlanSys2 with this action hub that you presented. I think that could be a nice combination to come to a kind of streamlined interface, how to integrate different planning technologies in one coherent framework for us. I think that's a nice combo that has been presented in those talks, in those two talks.
Yeah, I think one thing that was mentioned early on in this meeting is the kind of the need to, I don't know, collaborate on interfaces. And I think one such thing is going to be related to task and motion planning, right? Right now, I think a lot of the kind of messages and services, whatever we pass around, probably assume, a discrete set of symbolic parameters for actions. And that would have to change for task and motion planning. So very interested in keeping that discussion going.
Okay, great. Glad to hear you.
To add on top, actually, it is one of the topics that is recurring in AIPlan4EU. It's not so easy to come up with a general interface, and actually there are like different ideas because in the end, Python is pretty generic, so to speak, and that's why we went and said, okay, let's use PDDL as a first general interface, but then if we want to go further, there is still some question marks. So there are definitely some people in the AIPlan4EU community that are definitely interested in this problem.
Yeah, that's why I also wrote on the introductory slide on a very abstract level, probably because, as you say, it's not like with, for example, this recent app on HRI, which defined very concretely the topics and types. That's here a different level, yeah. That could be something for the next meeting, Sebastian, that you present this work. I mean, I think first step is that we get an overview to understand also the broad spectrum of use cases and needs.
Yeah, I would love to do that, and I will have my access to my camera next meeting, I promise. That sounds great.
Perfect. Deal.
Davide, that would be great, yeah. You may also, I put on the agenda, I added an item called action items at the bottom, or a section called action items at the bottom. If you could already type the title there, then we can put it on the agenda for the next meeting.
Great.
I have the other part. I can send you and we can fuse.
In this case.
Okay. Yeah.
Yes, you were asking about the task and motion planning. So we don't have the interface to PlanSys or to ROS, but the UPF, so there is a plan on the UPF to support this kind of planning. As far as I know, yes, but it's still it's still in design phase, so I don't know where it goes.
Christian, I remember I tried to bring a list of libraries like PlanSys2 on the official or the main docs.ros.org page, where they said they don't want to put, let's say, each individual work there. Of course, the ROS index for those packages that have been officially deployed on the build form, but perhaps we could create something like this awesome blah 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 list, the awesome robot deliberation list, and use such a repository with a markdown file to collect all the different packages, perhaps in some ROS deliberation WG organization, or we go for the convince purge in the beginning. Would be, I think both would be fine, but then we have a possibility for everybody here in the round to add further packages or pointers via pull request. Thank you very much.
Thank you.
Thank you.
Thank you for
Bye.
organizing.
Thank you. Bye.
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 Thank you.
Hi.
Hallo.
Ja, Michaela war ganz fleißig am Tippen. Oh, da war ein schöner Start, hat mir gut gefallen. Gute Beteiligung. Oh, haben wir die Namen eigentlich alle erfasst? Wahrscheinlich nicht, ja.
Kannst du das irgendwo noch raus extrahieren?
Ah, das stimmt. Manchmal kriegst du ja so eine komische Datei am Ende von dem Teams-Meeting.